Hello everyone, myself Dr. Syllabus. So I am going to take the course related to the PG, that is the Advanced Power System Analysis. So here I am going to discuss the basic objectives, course objectives of the power system analysis, and then basic power flow equations. So before proceeding this one, so we give the basic objectives of the this lectures. Here we have to just discuss the details of the syllabus contents, then course outcomes, then basic equations. So here advanced power system analysis syllabus is divided into 5 units. First unit we will discuss the load flow. So what are the load flow objectives? Why we are going to perform the load flow of any power system network? What are the load flow equations and building algorithms of the admittance matrix? Why we are going to refer the or why we are going to use the admittance matrix? So we will cover these terms in unit 1, that is the unit name is called as the load flow. So there are there are a few algorithms. These algorithms are iterative natures. So in this syllabus, that is the Newton-Raphson method, fast we can say that the decoupled Newton-Raphson method and fast decoupled method. These three load flow methods we will discuss. Now come to the second unit. Second unit, you can see here, second unit is the DC power flow. So DC power flow, when we are seeing the DC power flow, so here we have to first what are the assumptions are there. We will discuss the what is the assumptions. Then basic equations of the AC and DC power flow. From the AC power, what are the assumptions we have to apply to convert into the DC power flow? Because the in load flow power, there are a Newton-Raphson method, decoupled and fast decoupled method. So these equations are non-linear and iterative natures. So if we want to the very fast way to all information of the buses in the network, so we have to assume some assumptions. So based on the assumption, we can convert into the form of the DC power flow. So this have some sequential solution techniques, and this sequential technique can be applied for the multiple and empty DC systems, and also we go for the DC convergence tolerance. Then fault analysis. So fault analysis, we are classify the balance and unbalanced, and based on the unbalanced voltage means line to ground fault, line to line fault, and these unbalanced faults we are going to solve using the symmetrical components, just bus calculations, unbalanced and short fault analysis, and balanced short circuit analysis. And further after that we will discuss the load open circuit fault analysis. Then after that we will discuss the optimal load flow analysis. What is the difference between the unit 1 and unit 4? Here we are using the optimal word. Optimal means we are going to optimize either the operating cost or maintenance cost. So based on these optimal constraints, and we have to formulate the objective of the cost in terms of the generation cost or in terms of the profit. What are the constraints we have to consider? So all these are terms comprised in the optimal load flow analysis. So there are two methods of this one, that is the gradient optimal load flow solutions and Newton-Raphson load flow, Newton optimal load flow analysis. And we have to also consider the losses of the transmission line. So fifth unit is the compromise, that is the state estimation. So here why we are going to estimate state estimation in the power system? Why we are estimating the power system? What are the objectives? So there is one basic method that is called the least square method, and this is least square method we are estimating the all state values of the power system, because when we are measured the signals or measure data at the remote terminal unit and then send back to the control system or control center. So we are not going to directly apply this measured data. It have some bad data or some errors. So we have to filter out these data using the state estimation. What are the statistics and errors in the state estimations? And here one most important is the formulation of the Hessian matrix. And also we have to going to discuss the effect of the bad data in the estimation of the power system state. So here based on the syllabus contents we have defined the course outcomes. So here the totally 5 course outcomes are there. After the completion of this course, student can able to understand importance and admittances matrices in the power system and its use in the AC and DC power flow analysis, and also it is applicable for the optimal power flow solutions. Then second course outcome can be identify the different types of the faults and needs of the state estimation in the power system, and also analyze the AC and DC power flow algorithms, optimal power flow solution techniques, different faults in the power system networks. And we can further add the fourth course outcome to a student can able to solve the load flow equations using different conventional and non-conventional algorithm with proper formulation of the admittance as well as impedances matrices respectively. So here I have considered the conventional and non-conventional. It can be divided into the iterative and non-iterative algorithm based on the available measurement data. So apply the knowledge in regarding to the power system analysis in the planning and scheduling and reliability, security and control of the power system. So this is the all about the course outcome of the power systems. So here the first we are going to define the what is the load flow. Why we are going to study the load flow. Why the power engineer give the more impact on the load flow. So as you know that the load flow analysis is the backbone of the power system analysis. Why it is called as a backbone? Because it requires for the planning, operation, economic scheduling and exchange of the power between utilities. So also it gives a knowledge about the expansion of the existing system and also in the design stage. Suppose you want to go for the expansion of the network. So you can operate, you can perform the load flow analysis on the network. And also it is applicable for the steady state analysis of an interconnected power system during the normal operating conditions. Using this analysis, we can compute the steady state voltage and voltage angle between all buses in the network. Actually, using the load flow, we are trying to calculate each bus voltage magnitude as well as angle, means phasor value of the bus voltage. So this is our objective, and we have to also calculate using these phasor voltage values or the real and reactive power flow in every transmission lines transformers under the assumption of the known values of the generation and load. So also we can calculate what are the loading condition of a particular transmission line, what are the status of the circuit breakers. So these are the basic concept we are performing. So now come to the here this main top basic way to identify the conventions of the sources and load in the AC network. So in this slide you can see there is a device, it may be source, it may be load. So here we are consider for the source. Source is able to generate the active power as well as reactive power. So this source may be generator. So this generator is connected to a particular gate. So a particular bus, suppose ith bus connected a generator is there. So this generator generating the active power P and reactive power Q. So this P and Q are powers which is injected by the generator to the grid. So we have to consider this is the negative terminal. So because there is a injection power to the grid or to the bus, so we have to consider this is the negative power. And suppose a bus is there and we have to take the some power, or we have to connect or absorb the power by the load. So this power we have to consider the positive signs. So if any other devices like compensators or other, they are compensating or some devices, they can generate the reactive power, or some devices can absorb the reactive powers. So based on the power injection a particular bus, we can consider the positive sign or negative signs. So here for the generator, so we have to consider P and Q, or the negative means any power or any device are injected to the particular bus, so we have to consider negative. If that power taken from the bus, we have to consider positive. So like that we have to consider this value. Here we are going to discuss the power triangle relationship for a inductive circuit. So you know that this is the circuit where we are using this one. So this is the power triangle. So this is the apparent power, you can know this is the apparent power, and this is the reactive power, and this is the active power. So we have to, these active and reactive power are represented in the form of the triangle, so that is called the power triangle. So here you can calculate the power factor using this power triangle cos theta. This is the angle between the active power and apparent power. We can take the cos. So this is the power factor we can calculate. So FP, this is the power factor 1, indicates that the circuit is totally resistive. There is no inductive path. There is no reactance. So all voltage and currents are lies on the same phase. So there is angle will be 0. So this is the way we can find for the inductive circuits. You know that the voltage is V is when we are drawing the phasor difference between the voltage and current which is flowing through the inductor. So you can say we are getting the theta. So theta is the angle between the voltage and current with the voltage as the reference phasors. So here we can see represent the inductive load. Inductive load can take the reactive power. It absorbs the reactive power from the grid. So inductors absorb the reactive powers in terms of the watts, because the I current means current flowing through the inductor gives the positive angle on the complex power phasor. So you can see this is the give the positive phasors. So measuring the watts indicate the inductive or lagging reactive powers. So if we are measuring this one, we can say that reactive power is the lagging case. So here we always try to minimize this angle deviation. So this angle should be will be 0. At this will be 0 means circuit behaves like a purely resistive. So at this case you can see the component of the reactive power part Qt will be 0. Only the active part will be there. So active power, that is the equivalent to the apparent power. So in the resistive load circuits, they can only absorb the active power. So there is a absent of the reactive powers. So based on the compensators or a capacitors which can able to generate the reactive power in terms of the leading case, where we can compensate or we can supply the reactive power demand in the network. So here I am just going to discuss the for the capacitive circuits. So here we can see this the capacitive loads are there, and this will generate the reactive power in leading case. That is, we are considering that this capacitive load is injecting the reactive power to the grid. So you know that the voltage and current relations. So here the current is leading with respect to voltage by angle theta. When we are taking this cos theta, that is the power factor. So using this Q factor, we can minimize this power. So this is the way we can convert this voltages. So here you can see, so measuring the negative bar indicate the capacitive or leading reactive power. Capacitive power factor called the leading power factor. So this power factor can be calculated using this formula. So FP will have a value between 0 and 1. So capacitive, means power factor, that is maximum value 1 and minimum value 0. So it lies between 0 to 1. So we always try to make the capacitor will be power factor will be equal to 1. So this is the A for the capacitive. So in this lectures, we have just going to discuss the single phase AC power relationships. Here we are consider the A load, that is the load. This is the load. So in this load, so you can see this is the load. This load can be a resistive, can be inductive, can be capacitive, or a combination of the resistive, inductive, capacitive. So I have taking the current IT and having the terminal voltage VT. So this IT and VT we are considering the RMS voltage and current. So this is the individual components of the loads are known or not known. We doesn't know about this load. They can be series, parallel, combination, or other devices. So total power consumed by this load we can write apparent power. Here S represents the apparent power, P represents the active power, Q represents the reactive power. So apparent power will be equal to P plus JQ. So what is the unit of the apparent power? We can write volt ampere, and reactive power in terms of the watt or kilowatt, and reactive power, that is the kilovolt ampere, that is called VAR. So we have to compute this apparent power in the form of the polar. So you can first represent the all voltage and current in the polar forms. This is the magnitude and angle of a voltage. This is the phasor. So phasor of the current can be represented in the polar form, magnitude as well as angle. Here plus and minus. So based on the leading and lagging case, we can consider the positive and negative sign. So here we are apparent power, that is equal to V into I conjugate. So we are directly putting here, and magnitude voltage, we are taking voltage as the reference, and we are taking the conjugate of the current phasor. So here you can see this is the plus minus, here the theta current becomes minus plus. Just we are taking the conjugate value. So when we are subtracting or calculating the or separating the real part and reactive power, you know that the apparent power at the real power is active power and reactive power is the imaginary part. So when we are separating the real part and reactive power, so finally we are getting this term. So this is the term. So P is equal to RMS value or magnitude of the RMS value, that is voltage and current. We have to product and take the cosine of the angle between the voltage minus plus theta I. If here we consider positive, then here we consider the theta is negative. If here we consider the negative, then here we consider the theta is the negative value. So based on we can calculate the single phase AC power. Now we are coming to the three phase AC power relations. So this is the three phase. This is the phase A, B, C. So here we are consider the star connected load. So this is the star connected. So here generally we are represented a source. So this is the three phase system. Each three phase have the angle 120 degree. This have the 120, this is the 120, this is the 120. And each source have the V voltage. V voltage means magnitude. Angle with each other is the 120. So total average power is the sum of the average power in all the phases. So previously we discussed this single phase AC power relationship. Here we are discussed the three phase power. If we are calculate the single power, then we have to multiply the 3, so that is give the equivalent 3 powers. But here the three phase system, so we have to add all the powers, that is the P is equal to PA plus PB plus PC. So total power is equal to PA, means active power in the phase A plus active power in phase B plus active power in phase C, that is equivalent to 3 times of the PP. PP means per phase power. Suppose we have to three phase systems are there, we have to calculate the per phase power and then multiplied by the 3, we are getting the equivalent power of the three phase system. So PP we can write 3 Vp Ip cos theta, which is already calculated in single phase system. So we are putting this one here. Theta is the equivalent angle between the voltage and current. So this is the one way. This is the phase voltage and current here we are considering. If we want to represent the line voltage and line current, this is the Vp Ip is the same, we can write this is the Vp, this is the Vp, and this is the Vp. If current flowing through this source, that is the Ip. So here the star connected, here the phase current is equal to line current, there is no variation. But in terms of the voltage, when we are seeing that this is the line voltage, if calculating this line voltage from here to B, we are getting this root 3 times of this Vp. So this is the root 3 times VL IL cos theta. This is the power for the three phase system. We know the VL and IL cos theta, we can calculate the power. So similarly we can calculate for the reactive power. So this is also we can calculate for the single single phase. We know that the power Vp Ip sin theta. So this is the, we are taking the 3, multiply the 3 because they are three phase system, that is equal to 3 QP, and we can convert this phase voltage and phase current in terms of the line voltage and line current. So this is the root 3 times VL and IL sin theta. So this can or we can obtain the apparent power S is equal to P plus JQ. P and Q we already calculated, we can put here. When we are putting and representing in form of the polar form, so you can represent root 3 times of VL into IL angle theta. So here you can know that we are getting, so this is the A per phase system when we are putting. So this is the per phase system. When we are phase apparent power we are calculated, we can put multiplied by 3, we are getting the actual three phase AC powers. So that is equal to the 3 times of Vp into Ip. P for the phase voltage value or current, and L, capital L, represents the line voltage or current. So we are getting this form. So this is the, we can say this is the power. So you can see the power can be calculated using the instantaneous phase voltage. Here this phase voltage we are representing using these terms. So this is the current. So each voltage and current here we are considering a proper balance case. So instantaneous voltage or instantaneous phase current we are calculated, and according to this we are calculating the instantaneous power. This is the PT is equal to VANT IANT. So each phase voltage and each phase current we have to multiply and calculate the power. So this lecture have the we have to already covered the course syllabus contents, and based on the course syllabus contents we discuss the course outcome, and then after that we discuss the power flow equations, that is the active power and reactive power. Thank you.